This question is from GATE 2017 Mechanical Engineering paper set 2, question number 34. Three masses are connected to a rotating shaft supported on bearing A and B as shown in the figure. The system is in a space where gravitational effect is absent. Neglect the mass of shaft and rods connecting the masses. For M1 equal to 10 kg, M2 equal to 5 kg and M3 equal to 2.5 kg, and for a shaft angular speed of 1000 radian per second, the magnitude of bearing reaction in Newton at location B is dash. Let's find out. Let's write down the given things first. We'll list the masses. M1 is given to be 10 kg, M2 is 5 kg, M3 is 2.5 kg. Then we have angular velocity omega of the shaft is given 1000 radian per second. We will also write the distance of each of the masses from the shaft center. So R1 is 0.1 meter, R2 is 0.2 meter and R3 is 0.4 meter. Angle between the lines connecting the masses are also given. Each of the masses are separated by 120 degree from each other. So we can write down the theta for each of the masses, but only with respect to one of the axes. So we'll take x axis, and with respect to x axis we'll write down theta for each of the masses. So for M1, if we are writing theta 1 will be 0 degree because we are taking it with respect to x. For M2, we take it as theta 2 and theta 2 will be 120 degree. For M3, we take it as theta 3 and this will be 120 plus 120, which is 240 degree. And according to this, we'll write down the values here. Now for this system to be in equilibrium, the equilibrium equation summation fx equal to 0 and summation fy equal to 0. These two equilibrium equations should be satisfied, or we can say that the resultant force, the net resultant force on the system must be 0. This means the same thing because resultant force is nothing but under root of summation fx square plus summation fy square. So if each of them is 0, definitely the net resultant force will also be 0. Let's check whether this condition is correct. So writing summation fx, the forces in x direction are component of centripetal forces of each of the masses in x direction, and we have to sum them up together. So we have to write summation of each mass into its distance from the center of the shaft into omega square, where omega is given here, angular velocity of shaft, into cos of the angle that it makes with the x-axis. So let's add each of them and find out whether summation fx is 0 or not. So we have m1 r1 omega square cos theta 1 plus m2 r2 omega square cos theta 2 plus m3 r3 omega square cos theta 3. Omega 1, omega 2 and omega 3, that is the angular velocity with which the masses rotate, will be same as with which the shaft is rotating, and therefore we have substituted only omega in each of the terms. Let's put the values and find out. First thing, we can take omega square common and then substitute each of the mass values. So we have 10 kg into R1 is 0.1 meter cos plus M2 is 5 kg, R2 is 0.2 cos of 120 degree plus M3 is 2.5, R3 is 0.4 cos 240 degree. Omega square into, now inside the bracket we will have 10 into 0.1, which is 1, 5 into 0.2 is again 1 into cos 120. Now cos 120 is minus 0.5. Then third term 2.5 into 0.4 is also 1. Cos 240 is again minus 0.5. So 1 into minus 0.5 is minus 0.5. In the bracket we get 1 minus 1, which is 0. So omega square into 0, summation fx is equal to 0. This we have proven. Let's also prove summation fy is 0. So to write summation fy in this system, we have summation of mr omega square. When finding out the component in y direction, it is sine theta. So doing the same thing here, we have again omega square will be taken common. 1 into sine 0 plus 1 into sine 120 plus 1 into sine 240. So substituting the values, sine 0 is 0 of course, plus sine 120 is 0.866, which is root 3 by 2, and sine 240 is minus root 3 by 2, so it is minus 0.866. So here also we are getting the sum inside the bracket to be 0, so omega square into 0 will be 0 again. We have verified that summation fx is 0, summation fy is also 0. Therefore, net resultant force on the system will also be 0. If there is no net resultant force on the system, then there is no bearing reaction also, because we don't have any load to put on the bearings here. As there is no external load between A and B, the reaction that the bearing will have to offer will also be 0. So let's go back and fill in the answer. The magnitude of bearing reaction at location B is 0. To learn about this topic in detail, you can refer to the NPTEL video, Module 3, Lecture 4, Field Balancing of Rotors. This lecture is from the course Lecture Series on Dynamics of Machines. The course is by Professor Amitabh Ghosh. He is from Department of Mechanical Engineering of IIT Kanpur. I hope this solution will help you clear your doubt. Thank you.